Hello, good evening. My name is Nathaniel Osgood. Within this video, I'm going to be introducing the use of Scala for expressions to show, give a bit of a glimpse of their power when used with monads in Scala. Monads are illustrated by many constructs in Scala, including such as try, option, either, and many collections, such as stream, are all monads within Scala. And we'll see that while the for construct is often treated as a sort of mistreated as simply as a means to perform sort of classic loops in a using a certain syntax, it can be much more than that. In order to demonstrate this, I'm going to call up my Scala expression. And the first thing what I'm going to do is I'm going to import certain libraries here. These libraries are going to be used by the example, and it's important that they be loaded in just so we can execute some elements that we'll be exploring. Now, within this video, I am going to be first showing a bit of a glimpse of the most compact notation we use with for comprehensions, and then trying to unpack that a little bit to help parse what's being shown for those who wish to wait longer. So what I'm going to show is a situation where we're going to successively read in integers, in this case from the command line. Could be from a file or some other source. Could be reading things such as web pages over the net, any of which could fail. The things we enter may not be integers. The things we read over the internet may fail. And we're going to read them using what's called a try construct. And we're going to show how the for expression can be used to process things using the try construct in a very powerful way. So here we're going to be reading in something, an integer, try to read it in, and try to parse it as an integer. That could fail. If that succeeds, and only if it succeeds, we're going to go try to read another integer. That too might fail. And only if it succeeds, we're going to try to read a third integer from the command line. That also might fail. And then finally, if all of those have succeeded just suitably, we're going to take the first two integers, take their sum, and divide by the third integer. That too could fail. C, for example, might be 0, and we could get a divide by 0 error. The remarkable thing about this code is its conciseness and the fact that it focuses on the main line of execution and yet robustly handles the error conditions attendant upon it. For example, failed reads on any of these places, a failed division here, in a graceful fashion. And that's really the power of this construct, or much of the power, is we can focus on writing the code in a way that's transparent, clear as to its stages, and fairly modular, and yet be assured that the error conditions will be handled. So having pasted this in, I am going to then, here we go, I'm going to then enter values for this, okay? So I'm going to enter 3 for the first value. I'm going to enter 5 for the second, that is for B. And for C, I'm going to enter 2. And indicate success with value 4 being returned. By contrast, if I enter, for example, a nonsensical thing for the first integer, ASDF, and press enter, it immediately indicates a failure. A failure because this try detected that readInt was unsuccessful. It casts an expression that's caught by the try, and that ends up short-circuiting the others. As it turns out, we don't even go on and try this. We don't even go on and try that. Rather, we end up simply in each of the corresponding constructs returning try, a try that's a failure, and it indicates the nature of the failure. I could similarly fail in the say the third one here, I could enter 2, 5, and I could enter again ASDF for the last one, and again we'll have taken the first two. This last one happens, it bombs out, it doesn't even bother performing that, and it gives me a well-defined error. No exceptions thrown here, no indications that the flow of execution has been thrown dramatically off in a way that requires try and catch blocks, for example, or if nested if statements. Let's try another variant of this. Here we're going to have something, we're going to divide 3, 5 for B, so A is 3, B is 5. C is going to be 0. We're going to have a divide by 0 here. What happens then? Well, we again get a nice well-defined returned value, just as we did up there, a try returned by the whole expression, indicating another type of failure, divide by 0, one caused by this place. This is a robust construct, ladies and gentlemen. It's something that, if there's a failure at any point, it gracefully handles it, yielding a try for the whole construct, which indicates the nature of the error. On the other hand, there's also a clarity to the exposition, which supports an easy understanding of what's going on. We're reading 3 integers in succession, and then we're dividing the sum of the first 2 by the third. What's going on here? This is a for construct. We have this unusual syntax. Well, it turns out that, again, while the for construct is often used just to capture loops, there's a deeper meaning to things. This very special syntax actually turns into, at an underlying level, a very regular nested construct involving successive calls to flat map and map. This is, in fact, what it turns into. And I could perform the same operations on this. Let's say do the sum of 3, 5 divided by 0. And you could see we get an arithmetic expression. Alternatively, I could do ASDF, and it will immediately short circuit and indicate, without even waiting for the others, that it's failed. What's going on here? What I had indicated that ends up being a sort of underlying representation of what's going on here. Admittedly, a lot more of a sort of puzzling thing to look at first glance. And indeed, this is one of the things that recommends this sort of syntax. It's clarity. But let's try to figure out what's going on here. So we have this nested series of flat maps. For those of you not familiar with it, try is a construct which is a monad. If we try to read an int, for example, if we return a legitimate one, we'll get a success. If we return a failed one, we'll get a failure, indicating that this has been caught. This was unable to do its job. This threw an exception. Try caught it. By wrapping it in a try here in this monad, we were able to successfully capture the value and return this failure not as an exception, but as a genuine first-class value, a value that we could then process. And one of the ways we could process values like this is performing the standard higher-order functions associated with them. So having read this, for example, we could end up doing a map with it. So having read an integer, for example, we could multiply it times 3. So I'm going to read the integer 4, and I'm going to map that to 12 here, for example. On the other hand, if that try was something that failed, we could see what happens here. I entered a value, and it immediately short circuits this map. It immediately short circuits it, yielding a failure. This thing yielded a failure, therefore, when we apply map to it, it simply returns a failure immediately as well. It's sort of short-circuited. We're not actually multiplying anything times 3. It realizes if a map of anything that's failed is a fail. But another thing we could do with this is, for example, we could go and we could perform a flat map. Okay. Now, the motivation for this has to do with in some ways with the limitations of maps. So look, suppose we wanted to take a map. Here we simply used an unnamed parameter. I could have done the above like this. We'll take in an int, and we'll multiply the int times 3. All right, that would have been the same thing as above. If I had entered 4, it would enter 12. If I entered something that was a failure, this would yield a failure. But let's suppose I had something here that itself returned a try. Maybe I, for example, once I got that value, I tried reading a second integer. Okay. What's going to happen now? Now never mind the fact we're not using a. But if we had this, if we had something that let's say returned a try here, or let's make it even easier here, something like that, a divided by a minus 1, maybe something like that, right? Here we're going to try to read the integer. We're going to map the value within the integer, let's say 12. I'm going to take that, and we're going to try this construct. If we tried to do something like that, ladies and gentlemen, try to wrap this in a try, we might, for example, enter 2 here, and we'll get out a success. But it's kind of an awkward thing. We have a success inside of a success. Why? Well, this try will yield a success. It's a is 2, and a minus 1 will be 1. So we create a try of 2 divided by 1. But that itself is a try value, and we're mapping this integer to a try value, this integer inside the try into a try value. So we end up getting a try inside a try. It's not good. If we have something here which is returning something that can fail, that is, it's mapped in a try, we don't want to use flat map. That's going to yield these nested things. We don't want to use map. That is going to yield these nested things. We want to use flat map here. Okay, and I'm going to put 2 here, and that's gotten us ahead. We're flat mapping it. We're taking what's inside of this already. If this is a success, we'll take what there, A, and we'll flat map it. So this actually returns a monad. It returns, in this case, try, and that ends up being the in this case, it's the value returned here. A try of 2, which is going to be a success of 2. So, in general, if we are going to have something that we wrap in a try here internally, we're creating a try, we want to call it with flat map. Okay. So here, I'm motivating the use of flat maps here within our constructs. So when we see this, okay, here we get a value from reading an integer. Now, if that fails, calling a flat map on it will, just like above, fail. And to show this, I'm going to, and now I'm in a bit of a pickle here. I am going to demonstrate this using our code from from above here. So we saw how that worked with a value like 2 entered. We get back 2. Suppose I entered ASDF. I get back a failure. Why? Because this failed, and performing a flat map with something that failed yields a fail as well. Okay, so it is here when I go to paste this in. Here we go. If this succeeds, I'll go into a flat map, and A will carry the value of whatever was read there. If this thing failed, flat map will immediately return a failure, and the whole thing will be short-circuited. Okay, let's go with the case, though, that where we have gotten something. What is A here? A was the value read from the int, assuming, in the case where it's an actual integer. What's going on here now? Well, now we're going to, having received that value, we're going to be processing it, but the first thing we have to do is try to read another integer. And having tried to read that, we're either going to get a success or failure. Now, if this is failed, if it's a failure, again, this flat map is all going to fail, and we're going to get back a failure here. That's going to be the failure returned to this flat map, and it's going to be the value returned for the whole construct. So once again, if we get a failure at this point, that's going to be the failure for the whole construct. But if we succeeded at this point, we're going to do a flat map, and now we're going to need this value b here. Okay, that value b is going to come from where? It's going to come from this read integer. So we're getting that from the second read integer, assuming that it's indeed not a failure, that it's a success. Okay, we've got our a's and b's, and now, well, we have one more time of read int. If that fails, get back a failure. Well, calling map in it will yield a failure. That's going to yield a failure for this whole thing. This flat map is going to return back a failure, and that's going to yield back a failure for this, and we're going to have, again, a failure for the whole expression. The failure is going to propagate from n. It's going to be the return value for all of this. Okay, all of those are going to be hinging on the value of this map, and if that's a failure, it's going to ripple right out. On the other hand, let's suppose that read int succeeded, that read int succeeded, this read int succeeded. We have our A and B, and now for this last one, because we're performing a map, we can get our C. And then we're going to perform this expression. Now, this expression might take a little bit of work to understand it, okay? Here again, I'm going to just bomb out of that for a second, and I'm going to create a little experiment here. So I'm going to try, and we've seen how try, for example, can handle successes and failures. If it's a failure here, it handles it as a failure. If it's a success, it handles it as a success for the whole expression. Let's suppose that we have something like a try here of 4, and we try mapping it to be whatever that value is, and we'll make it explicit here. We'll say a is an integer, and we try dividing a by 2. Okay. What do we get? We get a success of 2. Why? This 4 is bound to this a, and divide it by 2, and we get back a success. Notice we get back a success of 2 and not merely a 2, because after all, we're mapping a try. We're performing this operation sort of inside of that try. We're trying to divide whatever is in that try, the a, by 2, and it's all wrapped in a try. After all, we're mapping the side of the try just like we might map in a vector. For example, each element of a vector, it's still, we get back a vector. Here we're mapping the inside of the try, the value inside of the try, and we get back a try. Okay, now what would happen if we had an error here? Well, wrapped up in the try this operation, so we'll get back a failure here. Okay, so ladies and gentlemen, this map here, if this yields a failure, we'll get back a failure as the result of this map operation. Map operation will yield a failure. This whole construct will yield a failure. This flat map will yield a failure. This whole thing will this flat map will read a failure. This whole expression will read a failure. And we'll get back a failure. In short, ladies and gentlemen, if this fails, we'll get back a failure. None of the other readings will happen. If this fails, well, if read this one fails, before trying any of this, this flat map will simply return a failure. This one fails. This map applied to a failure will be a failure for the whole expression. So here, this construct is actually handling failures as values in a quite robust fashion at any point along the way. Even though we haven't put in place explicit error handlers, try and catch statements, if statements, these are all handled. They're handled, ladies and gentlemen, by returning here. I'm going to enter 2, 3, a false input. They're handled by treating the failures as a value, as values on which we can apply operations like flat map and map. We can't do that if we have a null. Call an expression on it. We can't do that, ladies and gentlemen, with an exception. We can't call a method on it, but we can do it on values like tries. And that's the beauty of this. We have a whole sequence of operations, and we get out a value that indicates failure or success. So remember that all of this is by way of explaining this pithy construct. You see it here before you. All that desugars into this, turns into this. That's what this means. And yet this for expression yields an economy of expression and a clarity of comprehension that's admirable. Here we have sort of the mainline flow, the sort of flow of operations sketched out one by one. We can operate on the values as if, these A, B's, and C's, as if they are the integers. Indeed, they are. These A, B's, and C's. They're the integers inside of these things. And we can combine them in nice expressions without writing something as wordy as this. And yet, just like the construct above, it can handle errors. An error, ladies and gentlemen, such as divide by 0, and that occurs, that afflicts it at this point, or an error anywhere along the way with any of these readints failing. It can be readily and robustly handled. Short-circuited, don't need to conduct the extra work, just as this short-circuited was. So whether we phrase it like this, or like this, ladies and gentlemen, we have robustness in expression. We have clarity in terms of the ways in which we handle errors. But this for expression allows a brevity and clarity of syntactic expression that's truly admirable. This is one of the reasons that for constructs are so highly recommended, ladies and gentlemen, for monads, like try statements, options, futures, and other constructs such as streams that also serve monadic purposes. I hope this introduction has given you some glimpse of the ways in which the for expression in Scala is more than simply a nicety for iterating over lists in a kind of quirky syntax. Rather, it provides us with a brevity of expression for monadic values that allow us to manipulate the values within them while carrying along the monads, while carrying along the whole tries here, along the scenes, carrying their information along, handles errors robustly, but allows us to really get to the heart of the computations that we're performing. Those are many of the features that recommend it within the Scala language, and analogs within other languages such as the do construct in Haskell. Thank you very much for your attention. I hope this recording has been of help.